Dear ladies and gentlemen, dear partners and sponsors, dear Formula Student community, family and friends. I am thrilled to stand here as this year's CEO of AMZ Racing and welcome you to our rollout of our new race car, Castor, here at Autobau. Today we celebrate the remarkable dedication and hard work of an exceptional team of students who have taken on the challenge of building an all-electric race car that is capable of autonomous driving. Looking back at the previous season, we encountered numerous of obstacles and setbacks, still feeling the aftermath of the pandemic. However, we have used these challenges as stepping stones, learning from our experience and working tirelessly. As a result, we accomplished the earliest shakedown of an AMZ car this April. I'm extremely proud what this team has already accomplished, especially having been part of the core team last year. Seeing the new team evolve and grow was really satisfying, and I'm looking forward to the journey that still lies ahead. In the next couple of weeks, we are going to have an intense testing phase in front of us, preparing for the events this summer in Switzerland, Austria, Hungary, and Germany. For this evening, we have an exciting program in store for you. We will start with a presentation about our electric car, followed by a demonstration of our autonomous driving capabilities. Afterwards, we will unveil our new car, Castor, outside and give you a thrilling driving show. After the show, we invite you to join us for an apéro, and for those who are interested, a visit to the museum, where you can get a close look of our cars, as well as having the opportunity to explore and appreciate the world of race cars here at Autobau. Before we start with the presentation though, I want to thank all our sponsors for supporting us throughout the season. With over 150 sponsors in our network, we are incredibly proud to work with each and every one of you. Only thanks to your generous support and dedication, we are able to present our new car here today. So thank you very much, and please enjoy the presentation.
Ladies and gentlemen, good afternoon, and welcome once more to the rollout of Castor. My name is Yannick Feuillet, and this is my colleague Lucas Gibson. Castor is the 16th car in the history of AMZ Racing. And as you just saw in the video, the association has come a long way since its inception in 2006. We started building combustion cars, but soon switched to an electric powertrain. And since 2017, we have been developing autonomous systems, dominating the category in the first years. This history is a legacy that we are determined to build upon this year. You may wonder how the name Castor came to be. Like the 15 cars before it, Castor is named after a Swiss mountain, itself named after the Greek mythological twin half-brother and one half of the Gemini, Castor and Pollux. At 4,223 meters tall, Castor is certainly an imposing mountain, which is part of the reason we chose to name our car after it. Now, I'd like to talk to you a little bit about the project from our perspective. For those who've been following the project and seen the amount of hours that we have put into it, I want to give some insight into the things that have been motivating us to keep pushing as relentlessly as we have. We all joined this endeavor with a shared dream. We didn't set out to build a race car for any reward, but for the chance of a lifetime, to push ourselves to and beyond our limits, and to be part of something bigger than ourselves, to see what we could accomplish as a team when everyone goes all in. Dedicating a year of our lives to this shared dream continues to be rewarding in ways that are impossible to put into words, and we are deeply thankful to many people for their support. We have our sponsors, our alumni, and experts from both the industry and our universities standing behind us. With their expertise and support, we have been given the tools and guidance that we need to build our own car. And so we did, which brings us back to Castor, a car built with one idea in mind: to go as fast and perform as well as we possibly can. And with a summer of competitions all over Europe ahead, we are intent on bringing the fight to our fierce opponents. Success at these events won't come easy, and we are determined to push until the very end. And with that, I would now like to hand over the floor to my colleague Lucas Gibson, who will tell you a little bit more about what sets us apart from the other teams and how we plan on beating them.
Good afternoon, everyone. Now, before we get into the more technical details of our car, we would like to give you a little peek inside what it was like for us to be part of the team that built Castor. The recent merge of the electric and the driverless categories has brought a new challenge to the Formula Student competitions. This meant that Castor had to be able to provide a comfortable and a reactive driving experience while seamlessly integrating the autonomous systems. This challenge affected all parts of Castor: the mechanical, the electrical, and the software infrastructures. As a team, in the diverse backgrounds and interests of our members, attracting young engineers from across the world, from the northern and colder regions of Norway, all the way down to the climates which are a bit warmer, for example, India or Cyprus. This diversity fosters an environment where we, as new team members, can feel at home in. Working alongside veterans of the community who can give the guidance and advice that we need, all the while still having the freedom to push our own ideas, explore various concepts, embrace challenges, and evolve our skill sets. So day in, day out, we found ourselves here in Switzerland, working in our workshop, standing shoulder to shoulder and building something which encompasses our general knowledge as engineers, our determination to continue and push limits, as well as our relentless pursuit of perfection. Castor boasts all the excellent features AMZ cars are known for, featuring things like the hydraulic suspension and the power-dense motors. So combining our strengths together with the driverless team, who is renowned throughout the Formula Student competition for its prowess, we hope to achieve a successful season, especially in the coming months with the testing. Now, let's delve into some of the technicalities and engineering behind this car, starting with one of the biggest components, the chassis.
The chassis is in many ways the centerpiece of the car. Every component, from the aerodynamic devices, the suspension, the powertrain, to all the electronics and parts needed to make the car drive autonomously, is attached to or housed within the chassis. The use of a carbon fiber monocoque with a lightweight aluminum structure, a sandwich structure, has allowed us to build both an extremely light chassis at only 16.5 kilograms, but also crucially one that is outstandingly stiff. The introduction of a dedicated systems engineer for this season, in charge of the packaging and handling of important interfaces between different modules, has allowed us to make the most out of every bit of space inside the car. Furthermore, optimizations in the manufacturing process, as well as a united team effort, have allowed us to build this crucial part earlier than ever before, with the chassis being demolded on March 8, 2023. It's a tremendous achievement and one that continues to contribute to the excellent progress that we have been making so far. The next parts that are most noticeable when looking at the car are all the parts of our aerodynamic package. Their goal is to generate so-called downforce. Amongst others, Castor features a rear wing with 3D end plates and a side pod, which serves an important role in the car's packaging concept. The wings on the car work much like those on an airplane, just the other way around, pushing the car into the ground instead of lifting it up. The side pods also exploit the so-called ground effect, where their proximity to the ground creates a low-pressure zone beneath the car, pulling the car onto the ground. In order to maximize the aerodynamic grip generated, computational fluid dynamics were used to simulate the performance of the package and optimize every last detail of these components to manipulate the air with great efficiency. These efforts enable the car to generate around 250 kilograms of downforce at a speed of 100 kilometers an hour. To put this into context, this means that Castor could drive upside down at 100 kilometers an hour. The downforce a car produces is sometimes also referred to as aerodynamic grip. as it increases the forces that the tires can generate. The other kind of grip, called mechanical grip, refers to the traction that the tires and suspension can generate on their own. So, the purpose of the suspension is not only to attach the tires to the chassis, but indeed to get the most out of the tire potential. This is done by affecting how the suspension behaves when moving in certain ways and at certain speeds. Castor once again features AMZ's trademark hydraulically actuated mode decoupled suspension with warp decoupling. This unique system reduces the wheel load variation and thus increases the grip that tires can generate, while enabling us to tune the car more easily without the need to make as many trade-offs between outright performance and drivability of the car, giving us a considerable advantage compared to classical suspension systems. The double wishbone configuration using carbon fiber tubes also optimizes the weight of the entire suspension. Now, all of these parts serve to optimize the way that our tires interact with the ground, but the system would be incomplete without our so-called wheel packagings. They form the contact between the tires and the suspension. Castor's wheel packages are optimized for our self-designed 10-inch carbon fiber rims and consist in part of an SLM-printed, topology-optimized upright and brake caliper and a milled wheel hub. They also house both our motors and our step planetary gearboxes, enabling us to deliver power to all four wheels simultaneously. Also worth mentioning are driver controls. They function as the interface between the driver and the car, translating inputs on the pedals and steering wheel and giving feedback to the driver. For the driverless functionality, the steering and brake systems also need to be able to operate autonomously. For the steering, a separate motor can take over the actuation of the steering and provide measurements to the DV pipeline. The autonomous braking system, on the other hand, is especially important to ensure that the car can be remotely stopped when driving autonomously. This year, we introduced a new pneumatic autonomous braking system, cutting down on weight while significantly improving the reliability of the system and lowering the required maintenance effort. So now that I've covered how we slow the car down, let's talk a bit on how we get it going in the first place.
The powerhouse of our cars and pride of AMZ are fully self-developed motors. They are capable of spinning at up to 28,000 RPM, which is revolutionary. That by I snap my fingers, they will have spun around their own axle 433 times. Being developed and perfected. Thank you. Hello? Okay. Slowly, continuously being perfected over the past 12 years, ever since we started building them, we have made sure that they can accelerate castor from 0 to 120 kilometers in less than 3 seconds. With one motor at each of the four wheels, the vehicle dynamics control algorithms use the throttle and the steering inputs and convert these into different torques. They can be individually applied to all four wheels to make sure that we can maximize our gain. Simultaneously, the torque vectoring algorithms create a yaw moment by shifting the applied torque between the wheels, allowing the driver to take swift and tight turns and elegantly maneuver the racetrack. Additionally, our motors have a power density of 17.75 kilowatts per kilogram. This is almost double that of the modern Formula electric competitions. What lets us control these powerhouses is our inverter. It's responsible for generating the alternating current which we need to reach our high torques and revolutions per minute in our motors. Our software is customizable, allowing us to adjust our communication interfaces and control algorithms on the fly. The inverter requires accurate signals from the motor's resolver in order to behave effectively and control our motors. For this, we designed our very own plastic optical fiber communication protocol. By using light to send our signals instead of electricity, we effectively make our systems completely immune to electromagnetic interferences. Every inverter is manually disabled, from tiny resistors over to large filters, giving us complete control over the manufacturing process. Equipped with silicon carbide semiconductor modules, we make sure to maximize our efficiency while still having the high switching frequencies. Providing the raw power that we need to power our motors, we have our in-house created high-voltage accumulator. Featuring 264 lithium polymer cells with an energy capacity of 6.45 kilowatt hours. It provides all the energy that we need to bring castor to life. With an impressive 22 exchangeable sub-packages, we make sure that the high-voltage accumulator is easy to work on and maintainable. Additionally to this, we have a smaller akku underneath the driver's seat. It is responsible for providing the power to the low voltage compartments of the car. Bringing this whole story together, we have the wire harness, featuring 350 meters in cable length and military-grade connectors. These connectors ensure that we do not suffer any connection issues through our drives, keeping our systems stable and reliable. We have various connectors and sensors throughout our car which can take in the log data that we need for crucial improvements in our performance. This is done by using an engine control unit. So, with each one of these modules being worked on by a dedicated group of people, we have managed to bring castor to life earlier than ever before. What started out as not more than a few simple designs and an idea was effectively set on track and drove its first lap on the 30th of April. But our journey doesn't end here. Looking ahead, our team is committed to further refining castor and push it to reach its full potential. So, without further ado, let's take our first look at castor.
Welcome everyone, my name is Asbjørn and this is Stan, and we would like to present to you the driverless features of castor. With advancements in technology the recent year, the competition is becoming more challenging and new disciplines are emerging. One of the most significant developments in recent years is the rise of autonomous driving. AMZ has been a part of this journey since the DV category was first introduced in 2017. We have not only been a passenger, but pushed innovation with our state-of-the-art solution, sealing the victory for the first 3 consecutive years. Autonomous driving has become part of the AMZ DNA, and we are determined to continue pushing boundaries for what is possible in autonomous racing, developing new and innovative solutions while creating a platform for students to excel and become world-class engineers. As many of you might already know, last year was the start of a new era in Formula Student. The independent DV category was no more and the competitions were merged. This means that each team competes with one car capable of driving both manually and autonomously. The driverless functionality is therefore fundamentally dependent on a working race car. And in a year with more functionality than ever, we have managed to achieve the earliest driving AMZ car ever. This has created a good foundation for the combined competition season to come. But before we go into any details about this year's innovation, I would like to shortly describe to you how the AMZ autonomous pipeline works. So it all starts with perception, which is seeing the world. Then the estimation module estimates the car's position within the world. And then lastly, the control module is responsible for controlling the car around the track. The perception module starts with the camera and the LiDAR sensing the environment. The camera creates a 2D image, while the LiDAR a 3D representation of the environment by emitting laser beams and measuring the time it takes for the beams to bounce back. Using a machine learning algorithm, we are able to detect the cones of the track from the camera image. Evaluating the point cloud from the LiDAR, we establish another estimate of the cones. The points from the LiDAR lying on the cones are then projected onto the camera image and fused together to give the most accurate estimate of the surroundings. And then the cones positions are forwarded to the estimation module. And here you can see a video of the perception in action, where you see the LiDAR point cloud on the top and you see the camera working at the bottom. The next step is then to estimate where the car is located in relation to the surroundings. But for that, we need more information. As a result, you can see the car is equipped with many sensors, and from these, we are able to estimate the different states of the car, such as velocity, acceleration, and orientation. Together with the perception of the world, the SLAM algorithm creates a map of the environment while simultaneously determining a location within that environment. From this map, we are also able to generate a path for the car to follow. And lastly, the step is then to control the vehicle. For this, we use a nonlinear model predictive control. Using the measurements of the car and the car dynamics as input to the MPC, we are able to predict the behavior of the car ahead of time. This is a great advantage and lets us optimize the car's behavior in different parts of the track to minimize the lap time. Now that you've got a bit better understanding of how the AMZ autonomous pipeline works, it's time for Stan to talk about this year's innovation.
Good afternoon, ladies and gentlemen. As we already explained, perception is the first step in our driverless pipeline. This season, we've made some exciting changes to our sensor setup. First, we've managed to make it 40% lighter. The total weight has been reduced from 1,650 to just 990 grams. Reducing the overall weight of the car resulted in an improvement of its acceleration and handling. These improvements hold significant importance, especially now that races and electric and driverless competitions share the same car. While the mass of the vehicle is less critical in the driverless competition, it plays a pivotal role for our human driver. This advancement ensures that our team maintains a competitive edge in both categories. But perhaps the most important change we've made this season was the introduction of monocular depth estimation. This process consists of running cropped camera images of cones through the ResNet-18 convolutional neural network and then processing the output with the perspective and point algorithm. This new feature allows us to accurately estimate depth from just a single camera, which improves to correctly identify cones and perceive the racetrack at shorter distances. It also reduces our dependence on the LiDAR should we ever be forced to drive without it. With these changes, our perception module is more advanced and efficient than ever before. We're confident that these improvements will give us an edge in this year's competitions. Oops. Now that we've talked about perception, let's talk about the estimation. Its core consists of SLAM algorithm. It takes as input the visuals from perception and the estimated velocity calculated from readings of various sensors, such as the optical velocity sensor and the inertial measurement unit. Given those, SLAM creates a map of the racetrack and localizes castor within it. This allows us to efficiently navigate and avoid obstacles. This season, we've decided to move to an implementation of the SLAM algorithm called ISAM2, which is faster and more efficient than the previous implementation we've been using, GraphSlam. ISAM2 is just as precise and accurate as GraphSlam. However, it only requires 10 milliseconds per single iteration instead of 35. This means we can process more data in less time and make more informed decisions about how we perceive or how we navigate the track. Overall, the estimation module is an absolutely critical component of our driverless pipeline, and with the new ISAM implementation of the SLAM algorithm, we're certain that it will perform better than ever before, allowing us to achieve our goals in the upcoming races.
Yes. From the map then established by estimation, we need to control the vehicle to follow the desired path. For this, we use, as mentioned, a nonlinear model predictive controller running at 40 Hz. It uses a mathematical model of the car combined with sensor measurements of the states to predict the behavior of the car a finite horizon ahead of time. This gives, as said, an advantage to foresee the car's behavior and optimize it to minimize the lap time. However, the model predictive controller does not work seamlessly out of the box. Its advantageous performance is achieved through tuning of the controller. This process can often be very time-consuming given the many tuning parameters and the non-trivial relationship between the parameters and the closed-loop control performance. Given the importance of testing time and the increased demand of testing castor both manually and autonomously, we have created a tool called the Auto-Tuner to make both the tuning more efficient, but also reduce the dependency on testing itself. The Auto-Tuner is an optimization algorithm that uses Bayesian optimization for automated tuning of the MPC cost function parameters. Bayesian optimization uses a performance function such as lap time to evaluate the parameters at each iteration. The performance function is considered a black box and modeled using Gaussian processes. After each Bayesian optimization iteration, the probabilistic model is updated with the sample data. Based on prior knowledge, an acquisition function of the performance model is then used to select the next set of tuning parameters. As the algorithm iterates, it will learn more about the system's behavior and the different performance of this MPC with different combination of parameters. The algorithm will then shift its focus to the parameter space, which is more likely to give an increased control performance. After a sufficient number of evaluations, the Auto-Tuner will then converge to optimal parameters for the MPC, resulting in an improved control performance.
So the three modules, perception, estimation, and control, together form the driverless pipeline, which controls the car without the need for human interaction. The question that remains is, what happens if one wants to run and test the pipeline without using the actual car? This is where the simulation module comes into play. It is an essential part of our development process, allowing us to test the pipeline in a safe and efficient manner without the need for a physical car. This season, we've made a significant upgrade to our simulation module by developing a brand new simulator called AMZ Sim. It's been designed to be modular and extendable, allowing us to swap out different components based on specific requirements of each testing scenario. Additionally, AMZ Sim features brand new features which were not available in the previous simulator, such as the ability to simulate with or without ground truth, adjust the amount of noise in the simulation, or use real-life sample tracks. With AMZ Sim, we can create a virtual environment that accurately simulates the track, surroundings, as well as the movement and sensor readings of the car. This enables us to test and refine other modules as well as tune parameters in a controlled environment before deploying them. By identifying and addressing issues early on in the development process, we can ensure that our pipeline is reliable and robust in real-world racing scenarios. Overall, AMZ Sim has proven to be an invaluable tool in our development process, and we are proud to have created a simulator that is both powerful and versatile. Ladies and gentlemen, thank you all for joining us here today at our rollout. It's an honor to have such a wonderful audience of our esteemed sponsors, supportive friends, dedicated families, and cherished alumni. Your presence here means a great deal to us, and we truly appreciate your support. Now, to further showcase the incredible capabilities of our car, we have prepared a video capturing the testing process it has undergone. This video will provide you with a close-up look at the dedication and precision that went into building this vehicle. We believe that it will both inform and entertain you. After the video, we invite each and every one of you to join us outside the building for an exhilarating test run. Buckle up and experience firsthand the power, speed, and innovation that our team has poured into this extraordinary machine. Once again, we extend our deepest gratitude to our sponsors, friends, families, and alumni for gracing us with your presence today. Let's make this a memorable event as we celebrate our achievements together. Thank you.
At AMZ, a test day begins with a mechanical check of the car, where we check the screws, the brake system in general, and the hydraulic suspension. After that, we move on to the throttle command, and finally, we carry out the car onto the track and proceed with our on-track testing.
Testing is done in order to maximize car performance. With tuning our suspension setup and our control algorithms, we strive to optimize lap time. Still, the highest priority while testing is the safety of everybody involved.
One of the most important goals of testing is to push every component to its limit and identify potential failure points. After a successful test day, we have gathered a lot of valuable data needed to bring the car closer to driving reliably at its maximum performance.
Deploying our driverless pipeline on a real car is much harder than doing it in simulation. That's why, parallel to testing with Castor, we investigate a lot of time in testing with last year's prototype, Bernina.
Yeah, for all those with us here, we'll see you outside in a few minutes. Hopefully it doesn't rain too much at the moment. And hopefully we also have some umbrellas that we can hand out. So we'll see you outside in a second.